So welcome back. We are continuing our journey on optimization. It's been a bit of a long one, and we're going to sort of wrap it up today. And I think today's class might be the most kind of exciting and eventful class out of all the classes in the course, because we're going to learn the main algorithms kind of used in machine learning, now called this like gradient descent stuff. And maybe before we do this gradient descent for the actual like estimate of our loss, let me just really briefly remind you what is happening in this stuff. And what I mean by that is we talked about the supervised learning stuff, and just remember our algorithm, or like, okay, I call this like the learner function, is this thing called empirical risk minimization, right? And how does this thing work? It takes in a data set. It's going to make an estimate. That's why we care about this estimate. Like, that's this L hat of F thing. That's why we care about it, because it's an estimate of the thing we really care about, which is L of F, the true expected loss, okay? And if this thing is actually close to the true expected loss, then all we have left to do is just solve an optimization problem. And that optimization problem is just pick the best predictor that makes this estimate the smallest. Okay, so, and then we just, now where we've been like, this optimization stuff has been completely focused on saying, assume we have a function, how do we minimize it? That's all we're trying to do. How do we search over this function class to pick the best f that makes this the smallest? And that's what we return to, which is we talked about the one way to do this was to just solve it analytically, or what I meant by that is just solve it with a closed form solution. So you just had some expression that you just evaluate, and then you get this f. That was that closed form solution stuff. But now we've moved on to this other method called gradient descent. And gradient descent becomes useful because you don't always have a closed form solution, basically. And there's going to be another reason it's useful, which we talk about very soon. Okay, so that's where we're at. We're trying to do gradient descent to optimize this thing. That's the second step of ERA. So let's do it. Oh, and maybe the only thing, like there was a lot of this like background of how do you do gradient descent and stuff and details, but really the only thing you needed to remember is that we're going to always use first order gradient descent. And that just has a very simple equation, which is the following, which says that you're trying to estimate W star, right? You're trying to get this W star. It is actually the minimizer of your function. And all you do is just iteratively apply this equation, which is you start with some W, you don't know, but you make a guess basically. And then to it, you subtract this thing called like a gradient step. And this is descending according to the gradient business. And all you need for that is just like the gradient of your function and the step size. And you just keep iteratively applying it. So that's like all you really need to take away from the previous class on gradient descent. So what are we going to do? We're just going to apply this exact same equation, but not with G, but with our estimate of the loss. Okay. And that's really the story of a lot of machine learning. Like you can, if you remember anything from this class, it's that machine learning is just minimizing an estimate of this loss function. And usually it's done with gradient descent. Okay, so let us do it. And to do it, I just remind you of some terms in the actual supervised learning setting, right? So we have this like data set. Looks like this. It has n elements. Beautiful. Okay, it belongs to this like feature label space. We're working with the regression setting. Okay, first of all, we have features. They're d+1 dimensional. Remember, the +1 is for that bias term. And we're working with the regression setting. So the labels are R, sometimes called targets. They're just real numbers. Okay, so I remind you again, this is regression. And then we chose, the reason it's kind of linear regression is because we started with working with just the linear set of functions for our function class. So this is kind of the set we're searching over of predictors. And this set was all of the functions, right? These things are functions from RD+1, so from features to labels. And what? And they're linear. So that means that each one of these, when it gets as input a feature, right, x, little x, it has the form of x transpose w. So it looks just like this dot product thing. And this W is called like a weight vector or a parameter vector. And it's, of course, an element of D+1 because it's multiplying the features which are in D+1. Okay, so this was our setup. This was called our linear function class. And then we had to choose like a loss function that we were going to try to minimize, kind of. And by that, the loss function is this little L. So what did this little L look like? Well, it took in 2 arguments, which is, I'm going to use here y hat. This is just like our predicted value. And it takes in the true actual label. And we're going to pick for this, the case of linear regression, we're going to pick the squared loss. So this ended up looking something like y hat minus y squared. Okay, this was called the squared loss. So this was our setting. And we've already seen exactly the same thing for the closed form solution. Okay, and our objective, which we have also solved for already in the closed form solution, our objective is to find W, this, okay. I just tell you what the equation is first. So we're trying to find the minimum of this L hat function. And remember, there's like this version of L hat where I plug in W instead of F, where W is then, okay, I define it in a second. But we're trying to minimize this L hat function over all W's. Okay, these W's are in RD+1, right? And we called this thing this W vector hat. And we used hat because we're going to use W star somewhere else later, but this is really the same thing as that like W star we saw above. It's just minimizing some function. And the last thing to maybe remind you of is like, what is this estimate that we have with a W plugged in? Well, as before, it's the sample mean, right? So it's like you have 1 over n in the front, and then you multiply by the sum from 1 to n of what? Well, the loss function, right? But now the loss function with this x, okay, I plug in everything explicitly. So it's the linear function here, right? This is all the functions we have from this function class are these linear functions. So I'm like using this W here means just plug in this function. And that's subtracted from y. And this is obviously for the ith index squared. Yeah, so this was our, okay, so this was our estimate of the expected loss. It's just a function. It's called the sample mean estimate. And we need to minimize it. And we can see it's a function of W. So if we change W, the predictor we have changes, which means that it's going to predict y, like yi's differently. And we want it to predict like basically each yi as close as possible. So if our predictor actually predicts something very close to yi, this term is very small. And then you sum up a bunch of small terms and you get something very small, which tells you that in a sense our prediction is good because we're predicting yi quite close to correctly. Okay, so now all that's left is to apply gradient descent to this problem. And how do you do that? Well, you have a function, and now we just need to apply the update rule. So let's do it. So yeah, remember we had a closed form solution for that. So we the closed form solution, I'm going to erase it in a second, but like it was something like this A inverse B thing, if you remember. This gave us the precise solution for this. And now we're going to solve this in a different way, in this iterative way. And then we'll talk about the benefits of doing the closed form one or this or whatever in a second. So at this point, you might be like, why don't I just always use the closed form like for this if I just have the exact solution? So we'll cover that in a moment. But for now, we try this different approach, which is this turns out to be called batch gradient descent. This is the usual naming of this you'll see in actual machine learning. So it's just gradient descent. And we'll talk about the batch part in a moment as well. And I'm going to abbreviate this as BGD. So GD is a very common abbreviation for gradient descent. And then there's this B in the front for batch. We'll see there's other things we can change instead of batch here. Okay, so let's just apply it. So we need the update rule. So what is this update rule? Well, the update rule is, you might remember, it's just this thing. It's the weight vector at time step t+1 is, well, it's the weight vector at the previous time step minus this gradient descent step. And the gradient descent step was like a step size eta times the gradient. And now our function here is L hat of W vector at time step t. Okay. So this looks exactly like before, except this is now not G, but L hat. Okay. So now, like, to do this update step, all we need is the gradient. But in the closed form solution thing, we already computed this gradient, so I'm just gonna like remind you what it is and not compute it. But yeah, we computed this we computed all the partial derivatives, which means we really have the gradient. So I just tell you what it is, and I remind you. So this thing, right, is a vector. And the vector has as indices each one of the partial derivatives of L with respect to each one of the W indices. So W1, W2, up to WD. Well, actually, it starts at W0. That means it's the partial derivative of L hat with respect to W0, right? And this is a function of W at time step t all the way up to the derivative of L hat with respect to WD. And this is a function, again, of this W vector. Right, and this thing is just an element of R d plus 1. Should make sense in terms of like the types. They all match. This thing's an element of d plus 1. This thing's an element of d plus 1, right? It's a vector in d plus 1. So you just multiply by a constant. You still get a vector in d plus 1. So now you're just subtracting two vectors. What do you get? You get your new vector. This is your new W pointer. You remember in that, like, the plots we saw, it's just like you're moving closer and closer to W hat. So that's like, well, you should think about this. We're taking these steps that are moving closer and closer to W hat. Okay, and I just explicitly give you now the actual equation for this gradient. And after that, we have our gradient descent algorithm. And it's really that simple. So I will write that in a second as well. Okay. So this was the gradient. Okay. And it was the exact same thing, but with 0 replaced with d here. Okay. So we computed this in the closed form solution for linear regression part. But if you remember, you're just like, you looked at this thing, you took its derivative, the 2 like came out here, that's why there's a 2 out here. Then you took the derivative of the inside, that gave you a specific index of like this xi. That's what this was. So the 2 is gone, it's here. Then you took the derivative of the inside, that's where this came from, and you just repeated that for every single w. So it's a pretty straightforward derivative, actually. Anyway, so this is the gradient. So at this point, we have an algorithm. The algorithm is just iteratively do this some amount of times, and then stop whenever you want. The longer you do it, the closer you're going to get to W hat. So this is not far off from what a lot of the machine learning algorithms that are run in practice really are, actually. And so let me write it now. So now I give you the algorithm. And this is really, I guess, like a big kind of step in the course. This is a really like classic algorithm. So, okay. So this is an algorithm. And I'm going to call it, so it's called batch gradient descent. Okay, for like, this is for linear regression. So batch gradient descent, linear regression learner, right? So I'm defining a learner. The learner is this batch gradient descent learner. And in particular, I'm going to do the one, so I need to pick a step size, right? And I'm going to just do the simplest version, which is with a constant step size. But you can imagine, and you will do this in the assignment, which is that you can apply any one of the step size setting techniques as we described just literally right above here. Remember, there's these 4 different ways to select step sizes: constant, inverse decaying, whatever. You can just plug that into the algorithm however you want. But for the simplicity for now, we just use constant. All right, that's the start of the algorithm. So what does the algorithm look like? It looks very similar to the beginning is similar to the closed form solution one, I mean. So what is the input? As you might expect, there's a data set, right? So as we remember, there's like this learner that takes in the input, the data set, we're defining the learner. So this is like, we're defining A. Okay, we have a data set, and okay, as you saw, we needed a step size like thing. So in this constant step size case, we need to decide what is the constant step size. So like you'll pass this in as a parameter to your algorithm. Okay, so you'll pass in this eta. This will be like your constant step size that you're going to use. Okay? And you also need to decide like how many iterations you're going to do of your gradient descent thing. And that will be passed in as well, and that will be capital T. So capital T is just how many iterations do you do. And this has a name in machine learning. This is called not the number of iterations, but it turns out to be called the number of epochs. And so now these iterations of gradient descent have this name epochs. Okay, so remember this word. Instead of saying iterations of gradient descent, people say epochs of gradient descent, essentially. So that's a commonly used word. And so now we start, which is we start with setting we need to initialize our W. This is W0, but I'm not going to put 0 because we're just going to keep overriding it in the pseudocode. So we need to set W to something, but we have no idea like what to set it to. We really just take a guess. And by this, I mean we just set it to a random vector in RD+1. Okay, that should make sense. This was our W0. We don't know better. Like naively, we just set it to any random vector, and from there we're going to keep iterating until we try to get to W hat. And then that's all that's left is the iteration part, and the way you write that is as a for loop. So for t equal to 1, in Python you're going to write this as like for t in range, whatever, but this is how pseudocode usually is written. So for t from 1 till capital T, right? So you do this many iterations, number of epochs iterations. You literally just compute the gradient. So gradient of this guy. So you compute this. Well, what is the gradient? The gradient is this thing over here. Okay, and I can make this equation even simpler, which I guess I'll do to make it more clear. So I can take this term, and notice that it's the same exact term for all the things, right? This is the same as this, and so on. So I write a simplifying version of this equation. So I take that, I factor that out in front as just a constant number. And then what does this thing look like? So this is just a constant, and it's multiplied by x10 up to xid. But this thing is exactly the xi vector. Okay, so what we get is that the gradient is equal to this. Okay, very nice compact equation. So guess what? We're going to take this guy and we're going to plug it into our algorithm. This is the computation we need to do. Okay, so we set the gradient to that. And then what do? We do the update rule. So I can go ahead and literally take this update rule and copy it in. Okay. And then like in code, of course, this sum you might implement with like a for loop, or there's this thing called like doing it in a vectorized way. You'll see this kind of stuff in the assignment, but yeah, like it's as simple as just if you can compute this gradient and then do this step, this update rule, and then you just iterate t times. And once this for loop is done, what do? You return. And we need to return a predictor. So that's what we will do. We will return a function, f hat. This is actually the return value of our algorithm, A, right? Or sorry, of our learner algorithm. And that thing will just be x hat transpose of W. And here I remove these t's because in the algorithm, we just override the W over and over again. Okay, so it looks something like this. So in your code, like you wouldn't have like a new variable each time. You would just like start with W and then just keep overriding it, iterating and overriding and overriding, and then you output this. Okay. And like if you do enough iterations of this W will be close to W hat, like the closed form solution. Okay, so that's the algorithm. This is like an extremely commonly used algorithm, and all that, like, let me mention one thing, is like all that really changes in like more complicated machine learning stuff when people train things is, guess what? They pick a different function class here. It's not linear functions, it's, say, neural networks. Okay, all it is just this thing has a different form. It's this complicated, it's not, clearly it's not just x times dot, like it's not just a dot product, it's a bunch of other functions applied, but it's just another function of x. Then what do? You have to then take a look at what L hat is. So what I mean is L hat is not just like this simple thing, not the simple predictor plugged in. Now it's this complicated neural network plugged in here. But all the same, you still have just this function. And then guess what? The only thing that changes is that their derivative, this derivative, is now no longer this simple equation, but it's just a more complicated equation to calculate the derivative in terms of each one of these w's. But that's it. So then, like, although a change in this algorithm is this equation would be more complicated. And that's like called this back propagation stuff, whatever grade, like back propagation is just applying exactly this. Well, this derivative turns out you can think of it as like different, you can break it up into different derivatives at each, this kind of layers of neural networks. But all that really changes is this thing through the way that this predictor is different. And so the derivative is different. That's it. But this idea is very classic. If you, we'll see if we use it in later assignments, but if you use any of these machine learning libraries and stuff, you literally just like give it this, you tell it what your predict, like your function classes and stuff, and then it will even compute the derivatives for you, basically. And then you just like, your algorithm, you just implement this and just tell it like, oh, compute the derivative for me. And then there's always this step size thing, and it really looks just like this. Yeah. Do you still have a question? No? Okay. Cool. Can we write a summation? Can we write it as a summation from J from 0 to do for W? Yeah, so like you can, oh, you don't want to write, wait. So this thing needs to be a vector. So you wouldn't, I don't know if the question is something about like writing a summation from J equals 0 to D. Yeah, so this thing is a vector. So this whole thing is a vector, right? It's the gradient. So I'm just writing this in a compressed way. Oh, yeah. So I guess the question might be like, I can compute this vector by writing a for loop and updating each one of its indices one by one by doing like the update rule, exactly like you take this, the first index, you multiply by eta, and then you take only the partial derivative of the first index. So I could write a for loop and do that. It turns out to be less efficient, like in terms of computation-wise, to do that than write it like this and let the libraries handle the vector subtractions. But yeah, you could totally write this as a for loop just to like update each index one by one of the vector. Okay. So yeah, this is the algorithm. Okay, so we have two algorithms now, the closed form solution and the gradient descent algorithm. And at this point, you might be wondering, why in the world would I be running gradient descent for linear regression if I have the closed form solution, which was just like this A inverse B thing? Like, why do all these iterations, get to a W, and then this W is not even going to be W hat. It's going to be something very close to it, but it might not even be it. Yeah. So like, why do you iterate T times is because, well, you need to choose some number of iterations, right? And we know that if we increase T, then the solution gets better and better. Okay, and then the question is, how do you determine T? Well, you determine T by just simply usually plotting what you have in terms of like, okay, so you can then use this, so you get this predictor, and then you can just plug it in to this equation, right? And your goal is to minimize this function. So you can plug in the W that you returned, and you can just evaluate what this is. And so what you'll see in the assignment is what you'll usually do is you'll plot this equation for different values of capital T, or like you just plot it as T goes on. And then you'll, like, what actually happens in machine learning world is people will run this for days, this gradient descent stuff, and they have these live plots that'll show them like, I'm on epoch 10 billion or whatever, literally. And then they'll see that this thing if I were to like plot it with number of epochs, so this is like epochs, you'll see something like this. You'll have a very high loss, and then as time goes on, it'll get smaller and smaller and smaller. And then at some point, it starts being like, it seems like the iterations barely reduce the loss at all, and then you say, okay, let's stop training. And this is called training. This iterations is called the training part of machine, or the learning part of machine learning. So as the epochs increase, okay, so here's the idea. Yeah. Maybe this is very important. So like you're constantly out like producing new W's for each iteration, right? For each epoch, you're getting a new W, which technically you could have outputted each one of those. For each little t in here, you could just constantly could update every single one and see how good how good is it for minimizing this L hat function. And so this process of iterating is called the learning part, usually of machine learning. It's like you're constantly improving your predictor, and like the longer you learn for, the longer you run this, like the bigger the t is, the better of a predictor you're going to output. So this is kind of like how you view, and that, yeah, this is the way you'll view learning in the assignment 2 is you plot this thing with epochs. So you plot, as time goes on, you should see that your W that you're plugging in at the corresponding time makes this function smaller and smaller. So that's what learning really you'll see in machine. This is like, yeah, this is called like a loss curve. So you're plotting this estimated loss, and you see its curve, and you see it's decreasing with people. And we'll talk a lot more about this in a few more days, or in a couple weeks, I guess. Okay, so this last, I guess, half an hour is probably when you see machine learning stuff, you'll see a lot of this, probably like the most condensed amount of terminology. Okay. So anyways, the question was like, why didn't we just use the closed form solution all the time? And one answer I said is like, okay, sometimes there is no closed form solution, but here we had a closed form solution. And it turns out even here, there's like a reason to potentially still use gradient descent. And the reason is computation. Okay. And in particular, we're going to look at the computation of the closed form solution. Versus gradient descent. Okay. Really, it's this batch gradient descent. Okay. And out of curiosity, how many people here have taken like an computer science like algorithms course where you talk about the runtime of algorithms? Okay. Seems like a decent amount. But anyways, I'll review like the very quick thing. But the point is that we need some way to define computation, and we're gonna very high level talk about this here, and I just tell you some things about it. But yeah, this is all related to like this. Like if you want more background in this, if you ever take an algorithms course and you talk about the runtime of algorithms, this is like where all this is coming from. Okay, so some things. So like we can think of computation, or like here, we'll think about like number of computational steps. So we want these number of computational like steps to be as small as possible. And roughly speaking, this will be like the number of elementary operations. Okay. And these elementary operations are things like adding, subtracting, and we'll even do multiplying. Okay. Anyway, these kind of things. So you count the total number of these kind of things that are being performed by your algorithm. So like on a computer, you think of each one of these as being run in this thing called constant time. And then you just count the total number of these things, and then you can compare the two algorithms. Which one does more like addition, subtractions, like shifting, multiplying operations, because that's really all the computer is doing, and then you just compare the two. So that's all we'll do for these algorithms. And then there's going to be one more terminology you're going to need, which is like this big O notation for comparing things. Also, you'll see this in an algorithms course, but it's like the high level story is that you'll write something like f of x is equal to big O of g of x. Okay. And this means that f of x is less than, okay, f of x is less than or equal to some constant, so this is c, some constant, times g of x for some x greater than some x naught. Okay, so here's the high, like the high level thing in words is like this function, your function f of x becomes dominated or is less than some function g of x after some time point x naught. Okay, and you can scale the g of x function by some amount. So like for instance, I give you a very simple example of how we will see this a lot, is like maybe your f of x function is equal to, okay, maybe I use the common notation in algorithms, and I replace x's with n's. So you'll usually see runtime things talked about in n in this. And this is different from the n in our machine learning thing. Okay, so this is just like a sidetrack. So for instance, if f of n is like something like, let's say, n squared, let's say like 2n squared plus 3. Okay? Well, then you can write that this is big O of n squared. Okay, so this thing will be our g of n function. And why? It's because like, well, f of n 2n squared plus 3, well, it's less than or equal to, let's say, like 3n squared. So that's our constant. This is c. If n is greater than or equal to some n naught, I'm sure that after like 2. Okay, so if I plug in 2, what do I get? If I plug in 2, I get 2 times 4 plus 3, and that should be less than 3 times 2. Oh, 3 times 4. And that, of course, is the case because this is 11 and this is 12. Okay, so after 2, it becomes larger. So yeah, and like visually, what does this look like visually if I plot these things? So this 2n squared thing might be like some parabola that's growing and shifted by 3 like this vertically. And then this 3n cubed one would be a quicker growing parabola because of the 3 constant. Like this. And maybe this point is something like n not equal to 2, let's say. So the point is that after some point, this guy, so this is g of n equal to 3n squared. This guy dominates this function. It's always greater. Okay, so this becomes useful because like on the computers and stuff, we're going to count the number of like operations. Like for instance, we're going to do it in a second here. There's going to be like this thing multiplied by this. So there's going to be d operations, d plus 1 operations. This thing is of size d plus 1. You multiply by the same number, but then also you multiply this by this number here. So then you'd have 2 times d plus 1. And we don't want to just carry these constants around. So we're just going to say that, oh, this thing is big O of d operations. So okay, that's your short detour. In the course notes, I had a little bit more details, but here, so now I tell you what happens for the closed form versus gradient descent part. Okay, so now let's actually compare the computation of things. So first of all, for the closed form. So this is the closed form solution, and you might remember that that thing was equal to the following equation. Okay. And now I tell you, I remind you what these terms were. So this A matrix was equal to this summation from 1 to n of xi vector times xi transpose. Okay, and there was a b vector, and the b vector was also a sum I equal 1 to n of xi vector times yi. Okay, so now we just have to calculate how much computation does this take to compute. If you remember the algorithm was literally just solve this equation and then output. Okay, so all we need to do is just check how much computation this takes. And I guide you through how we would do this kind of sort of quickly. So it turns out that this thing called an outer product, right? It creates a matrix, a d plus 1 by times d plus 1 matrix. This thing turns out to take operations d squared because you need to multiply you need to multiply every single index of them. To create every index of the matrix, you need to do some multiplication. Since the matrix is d plus 1 by d plus 1, it becomes d plus 1 squared operations, so you get d squared. Okay. So then since there's a sum, you do this n times. So you would have n times d squared. So okay, the important thing is that, so I write computation. And for A, so computation for A, what does that look like? That looks like big O of n d squared. Should make sense. Then there's computation for B. This one turns out to be less than A, unsurprisingly. Here, this thing's d plus 1 dimensional. You multiply by a number. So that's just d plus 1. And then it's times n. So you have big O of n d. But we need the inverse of A. Right? So we've calculated A. Now we need to compute its inverse. That's another step, another operation. How much does that take? I just tell you that it's approximately, and you can make this, there's like a whole lot of research that goes into this and math here and stuff, but like it's approximately d cubed, it turns out, to take an inverse. Okay, so I tell you this. And so now, yeah, so these are the steps, and then you need to multiply like these two together. And I guess I tell you like this multiplication here is equal to d squared. Yeah. Okay, so turns out there's all these like operations and stuff, but at the end of the day, we want like the total computation. And so to get that, you just add all these up, right? Because like in the algorithm, if you wanted to, you could literally do all these steps like one by one. You would do like this, compute this, then your next step is compute this, takes that much time, then compute this, then the fourth step is compute this, and that's your W hat and output. Outputting takes also constant time. So total computation is big O of all of these guys summed together. So, and by the nature of this big O thing, you'll notice that this d cubed actually dominates d squared, so you can forget about it. And similar here, this n d squared dominates n of d. So this is actually just equal to big O of n d squared plus d cubed. Okay. That's the computation of this closed form thing. It's really dominated by, you have to compute A, which takes that much time, and then you have to compute A inverse, which takes this much time. Okay, so that's not very interesting until you compare it to another algorithm and then see how it does. And the other algorithm is gradient descent, of course. So now let's do it for gradient descent. Well, in particular, the batch gradient descent algorithm we wrote. Okay, so for that, we can just look at this like code here. So really like all the computation is in here. So you can see there's going to be this loop that's going to that's done t times. We'll add that in a second. Then there's this computation, and then there's like this step here. And I do this one a little bit kind of quicker. Okay, so yeah, so let's look at this thing. So this thing, it has like, this thing requires d operations. It's just a constant times a vector. Well, d plus 1, but we call that big O of d. This thing requires d operations. If you remember writing out the dot product, it's just the sum of d multiplications. So this takes d, this thing takes d, then we need to multiply this by this, which also takes d. So anyways, it's 3 times d. So you just have 3 times d, and then this is summed up n times. And then you multiply by a number. Okay. So the point is this, it's just n times something like 3d, which is just n times d. So computing, so for computing the derivative of L hat of W, well, that takes big O, and I shouldn't put equals. That takes big O of n times d. Now we go back. What else is left? Well, after that, we just need to do this update step. Right, we need to do this update step here. And this update step is just like a number times a d plus 1 dimensional vector. That's just d operations, basically. And then you subtract it from another vector. That's another D operation. This turns out to be big O of D as well. And okay, so then we're gonna, computing that is big O of D. And then you have this loop that happens T times. So the total computation is going to be this like T times this dominating computation here, which is N times D. Okay. Maybe I write all that. So there's this one more term, which is computing W hat. Right, this is like the iteration step. We said that was big O of D. And then there's this outer loop. And so after the outer loop, we get the total computation. And that becomes N times D times T. Okay, so these are the two things to compare, closed form and gradient descent. And so we're comparing big O of N D squared plus D cubed and big O of N dt. And to compare these, you can really just compare the two functions inside. So which function is bigger than the other? And that's what we very quickly do. Let me just, I guess, finish that. That's pretty straightforward, actually. So if the total number of iterations you're going to do in gradient descent is less than the dimension of your features, then this is very easy, and this is really the case we'll look at. So if this is true, then this, like, what's the runtime of gradient descent, right, is N D of T. But T is less than D. So clearly this is less than, and this is a little bit sloppy to write something like this, but okay, it's less than the following function, which is N D times D, which is just N D squared, right? I've just replaced T by a bigger number, which is D. And then, of course, this thing is less than or equal to N D squared and adding some other function to it, like D cubed. Okay, so what we got, this is the conclusion essentially, which is that batch gradient descent is more computationally efficient if T is less than D. This is the main case to consider. So like, yeah, it turns out that like, okay, in what is your dimension D? If it's a very simple case where you have like 3, 4, 5 features, this isn't so exciting. But when it's a much bigger problem, then this like can be much, much larger. You could have like thousands or tens of thousands of dimensions. And then T, maybe you only need like 10 or 20 iterations. And so then you definitely have quite a bit of a speed up. Yeah, there's some like, yeah. So that like basically like this gradient descent stuff can be computationally more efficient. And yeah, that's all I have to say about that. So that's like another reason to use it. But really, when you get into like more complicated domains, your function, the function class you pick is no longer linear. And there you can't even get a closed form solution. So you really have no option other than to use gradient descent anyways. Do you still have a question? Yeah. Oh yeah, so these are different. So this is called an outer product, while there it's a dot product. And so this thing, and I write it here. So like when we looked at this thing had something like X, I, W thing. And if you remember, this thing was really equal to like XI 0 times W 0 plus up to XID times WD. And you can see this is just D multiplications. So this one should be clear because you've seen what the dot product is. So it's just, the dot product explicitly is just a sum of D multiplications. So then the only question that should remain, which is why is this not D? And the reason it's not D is because this is not a dot product. There's something called an outer product. And the definition of this is like, it's more complex. The story is that like, it becomes a matrix. And each one of these indices of the matrix is like a more complicated story. This is like, it turns out to be like xi times xi0, and then it's like xi times xi1. And that's like only the first row or first column, and then the second column is like x. Oh, whoops. Okay, anyways, all I wanted to communicate was that there turns out to be d squared operations because you need to fill in a whole matrix. So it's like xi0 times xi0, xi1 times xi0. And you don't need to know any of this. But then it becomes xi1 times xi0, xi1 times xi1, and so on. And then you go this way and so on. So it's just a different equation for it. And that's it. That's all I have to, like, we don't need to talk too much about this. It's not like but the purpose is, yeah, it's just a different equation. When I give you the equation, you would find that it's a double sum. I can explicitly write this actually as like, okay, actually, this is a matrix, so I can, but like each index is defined by like a multiplication, and there turns out to be d times d indices now. So, yeah, that's it. How did you see that a is n d squared and other values in this complexity you're talking about? I can maybe very briefly talk about how a is this n d squared thing again. So this thing requires n d squared computations because if we look at it, I just tell you that this thing is d squared operations because the definition of it is a matrix that has d squared multiplications. Like each index is a multiplication, there's d squared indices in a matrix. And you do this n times. So then it becomes n d squared. And then the other question was, is this complexity of a program, or how did you get this complexity? What basis without seeing the program? Yeah, this is the complexity of the program. The program, we're using the word program and algorithm synonymously in this class, which is totally fine. And this is your algorithm. It does these operations. We can just talk about going from here to here, how many like elementary operations are there? That's all that we did, is we counted that. For the closed form one, I didn't but for the closed form one, we also had an algorithm. I very quickly remind you of that. It's here. And I did the same thing, but this algorithm was super simple. It was just like, well, I mean, you can see it. You calculated A. We talked about that computational, like the amount of computation for that. We calculated B. And then we calculated how much computation it takes to calculate the inverse times B. And that's it. So those are the so we just added all those up. So and then we compared the two. Okay. So we are talking about the amount of computation it takes to run two different algorithms. Yeah. 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 Right. So this thing gives you a number. And then it's just a number times a vector. So you can think about that like if we were to, where is that guy? Okay, then there's something like, let's just do the yi times xi vector part, right? This thing is a number, this thing's also a number, we can talk about each one. This thing, you can like visually see it as, right, writing xi0, xi1 up to xid, and multiplying it by yi at every index. That's what it means to multiply by a scalar. And so what do you have here? You have like d multiplications. That's it. So that's why this operation is d computation. And when you compute this, it just becomes a number. And then you just have a number times this thing, or times this vector. So instead of yi, replace yi with this. This is just a number. And then you have d operations as well. So in total, there's 3d operations. So there's, so like this guy is big O of d. This guy is big O of d. And then there was one more step, which was xi transpose w times xi, which is also big O of d. And then you have them all ultimately. Okay, but really this is just to emphasize like that, there was a reason to kind of even do this for this setting. If your dimension is large, then like it can be valuable if you only need a few iterations. Okay, but you might not be convinced yet. And so like you might have okay, there's a question which is like, can we do even better? And it turns out we actually can kind of do better in terms of computation, and we're going to trade off like somehow the quality of the optimization. And this is in terms of computations. Of compute. Okay, and here we actually really get into the kind of like the real algorithm that gets run in machine learning. And so usually, okay, what do I mean by like what here I give you some motivation. So what is not usually done? What's not usually done is you don't have this enormous sum from I to n. Okay, so like what you don't usually do is okay, so imagine your data set is like 1 trillion like words from the internet. Okay, so you have like these or 1 trillion sentences or something. So like to take one step of this, what you would have to do is you would have to compute this sum, which would have to take you'd have to sum up 1 trillion things just to calculate one gradient and to take one step. Okay, so there's the solution to this is that instead of estimating L hat using, okay, so instead of having L hat all the way up here, which is, we started saying like, okay, let's have this sample mean estimate of L hat. But if n is really, really large, then this estimate is then you have to do the sum is very long, right? You sum up n things just to get one estimate, and then you can take finally one gradient step. Well, it turns out the solution to reduce the amount of summing and computation is instead of going all the way to n, you break it up into chunks. And these are called mini batches. So here's the word where batch came from. So we think of this word batch as telling us that we're computing the gradient with respect to the loss on the entire batch of data, 1 to n. I'll write all this in a second. And then next thing is going to be the next algorithm is actually going to be called mini batch gradient descent. And so now instead of using the whole batch of the data, we're going to break it up into these mini batches. And then we're going to now have estimates on each one of these mini batches. So it's not going to go to n, it's going to go to some smaller index. But the nice thing is that the sum is smaller. So you can take gradient steps quicker. You don't need to do as much computation to do this gradient step anymore because this n is now a much smaller number. However, you suffer in the fact that your estimate is worse. That's going to be the high level idea. So let's write all that. But the point is, yeah, n can be very large, and to take one gradient step, you don't want to wait forever to do that. So we do this thing called mini batch gradient descent. And this is really what gets used. And similar to the step size, there's a lot of tuning in the size of the batch. So we talk about how you don't know what step size you should pick. So what do? You just try a bunch of different step sizes, see how you do for each one of them, and pick the best kind of one. It's going to be the same story here. So the way, and you'll see in the assignment, you'll just play around with changing mini batch sizes and stuff. But turns out that usually the best size in terms of how fast you get to the minimum is not just using the whole batch, but it's something smaller. Okay, so let's write this. So this thing we'll call MB, mini batch gradient descent. And yeah, so we had the data set, and now I write the data set, it's the same data set, but I'm going to write it in a slightly different way for visual purposes. So instead of writing it as just one long tuple from left to right, I write it as in this column broken format kind of. So I start with x1 till y1, or sorry, x1, y1, up to x. Okay, so now I'm not going to xn, I'm going to xb, and b is just going to be the size of my batch. So I go from 1 to b. This is not the whole data set yet, of course. So there's still lots more of the data set. The next point is going to be x of b plus 1. And so for visual purposes, I write it below. Right? So I've just broken it up by writing it below to make it a little more visually appealing. And so you'd have this y of b plus 1, and then you'd have this all the way up to what? Well, up to x of 2b. Okay. And then you'd have y of 2b. And then you do this until you finally get to x of, and these indices can be very annoying to make sure you get the right, like +1, -1 in place and stuff. So yeah, just be very careful about this. But it turns out, so m is going to be the number of batches you have. B is the batch size. I write this in a second as well. But then you're going to go up to m minus 1 times b plus 1. And y m minus 1 times b plus 1. Okay. All the way up to, and then finally we get to xn yn. Okay, we closed it. So this is the whole thing. I just written it up in this like chunks of size b. And now I tell you the terminology, which is b. This is called the batch size, or actually, you should really call it the mini batch size. So these chunks are called mini batches. This is the mini batch size. And then, of course, if you have the mini batch size and you have the amount of data, well, then you can take n and divide it by b. And for now, just assume this is divisible into an integer. And that's m. That's going to be the number of mini batches. So this is the number of mini batches. Should make sense. And here you can see we had m minus 1. So n, what's n? N, well, n is b times m. So that should make sense. Here we were at m minus 1 times b. So here, this is equivalent, like this guy is the same in this case as m times b. So it'd be one full batch at the end as well. Okay, so for now, we've assumed that n over b is divisible. It's divisible and it gives you an integer. And we're going to fix that in one moment. But before then, I give you like a very explicit example. Okay, so suppose n is equal to 8, b is equal to 2. Well, then m equals to 8 over 2. And you have 4 mini batches. Okay, so then D looks like the following. It looks like x1, y1, x2, y2. This is really just rewriting the above, but like with actual numbers. This is x3, y3, x4, y4, and you have x5, y5. Okay, we're almost there. And then the last one, which is x7, y7, and x8, y8. Okay, so that's the thing. Apparently I highlighted my notes. So like, this is going to be your mini batch 1. This is going to be your mini batch 2. This is going to be your mini batch 3. And this is going to be your mini batch 4. And so like this thing is called mini batch 1. Then you have mini batch 2. Then you have mini batch 3 and mini batch 4. Okay. Should make sense. You just break it up into these batches. And I'll tell you what we do with the batches in a moment. But before doing that, I just tell you how we handle this case of when we don't get an integer for n over b. So in particular, n over b is not always an integer. Okay, so then what do? Well, we're going to do the kind of easy way out for this course to make all the calculations much simpler. And so, okay, so first of all, we need to define what m is then, which is going to be the number of mini batches. And what we choose is to round down. And so in particular, we're going to choose to call it the floor function of n over b. So if this thing is like some number like 3.7, we just say it's 3. Okay, so we round down. Okay, so this floor thing, what does it mean? It means round down to nearest int. Okay, and the implication we have is that if I then call this the number of batches, what I'm doing is that I'm not using all the data points after data point m times b. Okay, so we don't use data points after mb. So basically we don't use n minus m times b data points. Okay. And so is this terrible? Well, like this thing is always less than b, so at most you're missing out on like something that's smaller than one batch. If n is like 1,000 and your batch sizes are like 10, you're really missing out on 10, at most 10 data points or something. It's not a big deal. In practice, you'll find that people actually do use this last small little thing, but then you always have to, in your algorithms, you always have to write an if case, which is like, if you're at the last one, then handle it in a different way and so on. So like in terms of performance and everything, it really almost doesn't change anything. But in terms of writing it down, it's way nicer not having this if condition everywhere in your code. So for this course, we just don't deal with the last batch, but like it really doesn't take away from any of the understanding or anything. Like, yeah, you're just missing out on one small chunk of data. Okay, there's some, okay, I guess I'll answer the question. There's something about computation of like, if xi is d squared, then xiw should be, yeah, and I think the question was something about why is this not d squared? And the question is because of the order of like matrix, like operations here, which is you do this, you can do this first, right? This is the only thing that like this thing is a vector time, like this has no interpretation. So this is the dot, like, okay, maybe I write it like this. This is, you do the dot product first, this gives you a number, then you multiply your number by a vector. So this is not like the same, this thing, notice that w times xi, I give you one last thing, which is w times xi is not equal to w times xi transpose, which would be an outer product. Okay. This is just two vector, like this has no definition. This is like vector, like what, like, is it element wise? I don't, like, it's not even defined here. Okay. So this is how you interpret this. Okay, I'll keep going. So yeah, so we have these batches, but what are we going to do? Well, we're going to do exactly what I said, which is we're going to define a new estimate of the expected loss. Just as before, we had this L hat of W, but now I tell you it's estimate M, like index M. And this is going to tell you it's the estimate for mini batch little m. Okay, so we have a bunch of these mini batches. We have a total of M of them, capital M. So we can think about it indexing each one. Like for instance, little m would represent like mini batch 1 or mini batch 2. So I write it down. So it's exactly as before, but now instead of having n data points, you have b. The sum is now a little bit ugly because you have to get the indices right. And this is just like a delicate art of trying to remember which one, like if you got the minus ones and the plus ones correct half the time. So it turns out this is the equation. Be careful though, because when you implement this in code, notice that here, a lot of like for when you write things in course notes and stuff, a lot of the time you start with index 1, right? So I'm saying this is mini batch 1, mini batch 2, and so on. In Python, indices start at 0. So everything gets offset back by 1 as well. So like be careful about these kind of things. A lot of the time in notes, you'll see things starting at indices of 1. Because it's kind of weird to say like mini batch 0. But in code, things start from 0. So I think you don't actually need the -1 here anymore in the code case or something. But yeah, like these are like the delicacies that programming treats you with, is you have to do all these little handling of case. And usually this is where the bugs come up, because like otherwise most things are pretty straightforward to implement otherwise. Okay, so yeah, like the equation is exactly the same, except now you just do the sum over less things. So it's a sample mean estimate of the expected loss, but using only B, like a one mini batch of data points. Okay. And so M here, M is an element of 1 up to M. Makes sense. There's a capital of M mini batches, so little m just represents which mini batch we're doing this for. So you have this, you have a different estimate now for every mini batch. Okay, I tell you some implications of this. First of all, the not so pleasant implication of this is that, of course, now, since we're using less data points, okay, first of all, I tell you one thing, which is this thing, as I said, is a sample mean estimate of L of W, right? Just like the other one was also, like the original one was also a sample mean estimate. But okay, with B data points. But the sort of unpleasant thing, which is that L hat of M is a worse estimate than L hat of M, or L hat. Makes sense, we have less data points. Okay, so where's the advantage? The advantage comes when we write the algorithm. So like you can already imagine, like I'm gonna give you the algorithm just right away. So like what's the algorithm gonna be? It's gonna be the same one as before, except now we have gradients with respect to a smaller like this sum that's smaller. So it's okay, it's a worse estimate, but you can take that, like it takes less computation to compute this. So you can take more steps of the gradient descent. And to write the algorithm, it's as I can do it just by, I suppose, literally copying this one and adding one more for loop, which is the for loop over the number of batches. And this is called mini batch gradient descent. And this is the actual algorithm that will be used a lot of the time in machine learning. Okay. So this now is no longer called batch gradient descent. It's now called mini batch gradient descent. I say for linear regression because, right, we've taken specifically the derivative here for the least square, or sorry, the squared loss and the predictor that's linear. So that's why there's that word linear regression in there. Okay. So this is mini batch gradient descent. Okay, clearly I'm not done yet. I'm missing some things that I need to add. What else do I need to add? Well, I need to add a parameter to the input, which is now your choice, B, right, the batch size. So you choose the batch size now as well. Everything else is the same, but now I need to okay, so I had one thing, which is I need to compute the number of mini batches I have. So that computation was this floor function. This is the floor function of n over b. And we assume we have like n because it's in here. You can just calculate the size of your data set and you have b. Okay, so that's what's changed. Okay, but now I said that this thing is not n. It's this other new, it's a different thing. So turns out the gradient is essentially the same as before. So let me just say one thing. What I haven't done is I haven't told you what the gradient is of this. But since the equation is exactly the same, except with the sum being over some less things, it's exactly the same gradient. Hopefully you can believe that that's true. And in particular, the gradient becomes now not from I equal 1 to n, and not 2 over n. Okay, so it becomes 2 over b. Makes sense. And now, so I don't have to remember what this sum here is, I copy this sum. But that's all that's changed. Instead of I, so it's the same algorithm almost, but now the gradient is for a smaller amount of samples or data points. Okay, so that's good. But like, we need to, right, we have many batches. So what we have to do is we have to loop over all of those, right? We want to calculate the mini batch step, or like the step for each mini batch. So we need to add one more loop. So that's what I'm going to do next. So now I'm going to add a loop, which it loops over mini batches. So that's going to be little m, indicating the mini batch. And we go from 1 up to capital M, which is the total number of mini batches. Okay. So that's all good. Hopefully there's one more little thing that I'm going to mention in a second, but at this point, hopefully it all makes sense. All I've done is now, instead of taking gradient descent steps with respect to the derivative of like something that had n data points, now I do it with something that has b data points. And here I don't use the subscript m and stuff because once again, I'm just constantly overriding the L hat. So this L hat really is the like this L hat here, but I don't write the subscript in the code because once again, you just constantly override the gradient and keep doing the steps. Okay, so this is our algorithm. And now I just tell you one little point, which is that notice what happens here is that you're constantly using the same mini batches. So what that means is that you're constantly, like what you would do is you would take the gradient with respect to like this mini batch, and then this one, and this one, and this one, and then you would repeat and do the same thing over and over and over up to capital T steps. It turns out that like for estimation purposes and stuff, it's useful to not have the same mini batches at every epoch, but to shuffle the data, right, at every epoch, and then use the mini batches of that. So then it would be like, maybe this one goes here, and this one gets swapped to like here, and whatever. They swap around, but you still use the same mini batch size and stuff. All this does, like at a high level, is it makes this estimate slightly better than it was before. Because like at every epoch, you're now getting like a new kind of sample mean estimate with a different version of the data. Okay, so all that, the way to do that is quite straightforward though, thankfully, which is that before you, or like at the start of each epoch, right? So these are the epochs. What you do is you just shuffle, okay, randomly shuffle. And in Python, this is like one line basically. You just randomly shuffle D. Okay, and then everything is just indexing the data set, right? This I is indexing. So now like you just move around the points. So you still have like estimates that are of size B, that use B points, but now it's just like a different B points rearranged. And this turns out to be quite helpful. And we don't want to, like, yeah, there's a lot of like theory about why this is helpful and stuff. We won't cover it in the course, but yeah, that's all I wanted to mention. So in the code, you're going to have to do the shuffling. This is important. Okay. And now I guess we'll wrap up something with like talking about the computation part and we'll end there. Okay, so first thing, like I just tell you, which is that the advantage is M, right? This is the number of mini batches times T, number of epochs, is now the number of gradient descent steps. Before it was just the number of epochs. Now you take more gradient descent steps. You take M times T gradient descent steps. And there's some special cases of this. So this is just strictly more general than the batch gradient descent algorithm in the sense that if I set B to be equal to N, then I have one mini batch, and this gives back batch gradient descent. And then here's the one that, this word that you'll hear a lot in machine learning world, which is that if I set B equal to 1, so I set my batch size to 1, I have an estimate with just one data point each time. Then the number of batches I have is N, so each point you can think of as a batch, and I take a gradient descent step for each point as of like a point estimate. Then this gives something that's called stochastic gradient descent. And okay, so I write just GD for gradient descent. And in particular, this is usually said as SGD. And you'll hear this word a lot. People say like, oh, I'm using SGD for optimizing, whatever. And you'll even hear it overloaded in the sense that people, when they say SGD, they don't always mean B equal 1. For this course, will mean always B equal 1. But they actually just mean, oh, if B is kind of small, like if it's 30 or 60 or like 100 or something like that, like that's still okay. If your data set's like 1 million and something, then SGD just means like B is kind of small. So this is like the actual thing that people will call things. And then, yeah, and then like, okay, the computation should be pretty straightforward. We end with this thing, which is that I don't give you all the detail. They're in the course notes, but like it's almost as you would expect, which is like, okay, so for the mini batch gradient descent, you might remember in the batch gradient descent, we had this N Okay, we had like n times d times t, right? But now, well, let me just make sure I say this right. Right. So I could write it like this. We had d times n times t, right? But now n, well, what's n? You can think of n as being, okay, so first of all, n, you know n is equal to m times b, right? It's just the number of mini batches times the batch size. So you can write this as b times m times t. Okay, so it's really the same. Or like, if you were to look at the algorithm, what's happening? What's happening is that like you have this d times b operations for calculating the gradient. Before it was d times n. Okay. So what I mean is this thing takes d times b computation to compute. Before it was d times n. B for the sum, d for this. But now you have a loop over m and a loop over t. Before you just had the loop over t. So you get something like this. It turns out that this is actually like, so for batch gradient descent, we had something like this. These turn out to actually be equal for like, if you set all the values the same, if you have, so d will be the same, of course. N is your data set size will be the same. And if you set t the same for both, then obviously these computations are the same. But here is like it turns out like in practice, okay. So like what happens, so I ended here. So like in practice, for the same number of epochs t, right? So you run it for the same amount of epochs. It turns out the computation is the same if you have the same number of epochs. For the same t, many batch gradient descent usually finds a better W. So it'll get something closer to W hat for the same number of iterations. So this turns out to be like what you find, and this is in particular for the case. So this is the case if your batch size is strictly less than n. So then that means it's like, so batch gradient descent would mean b equals to n. So when I say mini batch gradient descent, I mean strictly less than n. So if I pick a batch size of like 30 and my n is like 1,000 or 10,000 or whatever, then it turns out that usually after the same number of epochs t, I'll get a better W. However, the computation for that t is the same for both algorithms. So for the same cost of computation, you get usually a better solution. And that's it for today.